Hello everyone, welcome to today's webinar, Optimizing Maritime System Design with LCM Insights. And LCM is of course Life Cycle Management. Thank you for joining us. We are honored to get to speak to you. Before we get started, I would like to go over a few items so you know how to participate in today's event. The webinar is scheduled to take about 50 minutes, and if you have any questions, please feel free to submit them as comments anytime during the presentation. We will answer them in the comments or reach out to you afterwards. Now, let's have a look at today's agenda and speakers. My name is Magnus Sörensson. I'm Director Business and Sales for Systecon's North America business. I'm also naval architect, and I have worked in defense and shipbuilding for over 25 years. I started my career as project manager for combatant craft at the Defense Material Administration, or FMV. That is the governmental entity in Sweden procuring all the equipment for the armed forces. I will start by giving you a brief introduction to what's unique when modeling naval vessels and naval system design. Then move on to breaking down top-level requirements and distribute them to relevant subsystems so we can model these systems in Opus. And finally, I'm going to say a couple of words about the importance of data-driven decision-making. Now over to my fellow colleague, Gustav Sölveling.
Hello, everyone. My name is Gustav Sölveling, and I've been with Systicon for close to 13 years now. I'm primarily a software developer working on the Opus Suite, but I'm also a frequent user of the tool suite, and I'm working pretty closely with our users out in the community. So in the second part of this presentation, I will switch focus a little bit and dive into Opus Suite in particular. So start by talking about Magnus's, tying together Magnus's design steps and how we can use Opus Suite to address questions in there. And in the last part, I will dive into SimLogs and show you a modeling example, a live modeling example where I navigate around the tool suite to give you an idea of how it can be utilized.
So, diving right into it. Naval vessels or ships are among the most complex systems that exist in the world. The ship is essentially a platform with multiple different subsystems that are supposed to work together seamlessly in challenging environments and under harsh conditions, many times autonomously and for long periods of time. And when we say naval vessels today, we refer to the big complex ships like aircraft carriers, submarines, frigates, corvettes, not the smaller patrol craft. So these big vessels are normally built in very small series or as one-offs. Not often you see prototypes, which means you have to get it right the first time. Hence, modeling is key. You want to verify and validate in the computer before you start cutting steel or invest and procure expensive equipment. These vessels are highly complex systems, including a lot of components, hence large computing models. They are also equipped for multi-mission capabilities such as anti-surface, anti-air, anti-submarine, naval mine warfare, escort, reconnaissance, etc. You don't have to get back to base to change mode. You can do that seamlessly out at sea. The operational profile comprises concurrent and or consecutive missions with basic functions running 24/7. And basic functions, that is the actual motor ship or the floating hotel caring for the crew. Another thing is that you often carry ammunition for both exercise as well as live ammunition, which means that you can change mode of operations very quickly. The crew lives on board, and you have on board support capabilities, spare parts, storage, supplies, and there's even possibility to replenish at sea, fuel, fresh water, or supplies. This means that you have a great autonomy and a very long range. The life cycle for these vessels are well over 25 years. You can see much longer than that. We have midlife and life extension programs. And the annual exploitation is from a smaller patrol boat around 1,000 hours to well over 5,000 hours for the bigger vessels. This will be an introduction to naval system design, and for those of you who are familiar with this, it will be a short recap. Ship design is an iterative process. You start with an assumption or an educated guess based on your customer's mission and operational requirements. Those requirements can either be functional and abstract, like system effect, or more explicit and hard requirements that could say to fit a certain system, whether it's a weapon system or a machinery. The idea of having abstract requirements is, of course, to encourage the designer or builder to find the best solution to your problem without giving them the solution direct. Based on these requirements, you start to establish a certain size and proportions for your vessel. You need a hull form that can sustain the seakeeping capabilities you want and the speed and other comfort criteria. Certain propulsion, are you going high speed, low speed, operate in shallow water, etc., or if you have noise limitations. Hull material and structure is an important part. Maybe you want to construct a vessel out of non-magnetic material or other qualities that will decide. How much payload do you need in terms of volume and weight? What is the light ship weight, stability, and finally the cost? Now you've done one rotation in what we call the design spiral, and you will go through many laps during the process and the different stages, going from concept design, preliminary design, contract design, and detailed design. As a naval systems engineer, you're involved in many different technical areas, from the propeller to the curtains in the mess room, we like to say. So to enable the analysis of top-level requirements, we have to break them down and distribute the requirements to the applicable systems and subsystems. To do that, we start by dividing each capability into different functions. And we divide the functions in main functions and basic functions. And the basic functions are always required. It's like the hull, your propulsion plant, power generation, navigation system, command and control, etc. Whereas various or 1 or 2, 3, 4 main functions may be required to fulfill each capability or mission type. Then, if you look to the right, we're going to break down the main function, and in this example, it's the mine countermeasure function into sub-functions like mine hunting and mine sweeping. And if in traditional naval systems engineering, you would now break it down to function group, a generic structure. But we shortcut this a bit and directly break down the sub-functions into subsystems, so we can model that in Opus Suite. So the purpose of system-oriented lifecycle management and LCM analytics is to increase vessel performance and availability over time. It's simply not enough to look at the novel system just off the production line. It is very important to understand what happens over time. After X amount of running hours and when the system is deployed in the theater, will it still have the acceptable performance and availability as originally stated? This is where we come in and can help you with Opus Suite can help you. And this is something Gustav will show you later on in our presentation and webinar. As the design process progresses, you commit to future cost, both capital expenditure, the cost for the actual vessel or technical system, but also the future operational cost. So the earlier you do this, the better. Early in the process, you may not have much detail of the system that you're designing, but it will do with a generic model and generic data. As the project progresses, actual data becomes more available, and you can use that to upgrade your model. So this is an iterative process as the design spiral, and this is supported by Opus, of course. So this was a brief introduction to naval design and what naval vessels are compared to other smaller platforms. One project among many others that uses LCM in a similar way is the new Danish patrol vessel project, where we, Systicon, assist with modeling, analysis, and simulation services. And this project is ongoing as we speak. So finally, before I'm handing over to Gustav, if you're interested what Systicon and Opus Suite can do and how we can empower your design process, I encourage you to look into our website, where we just published a new article from our fellow colleague Sara Lövdahl, who is talking more about what we can do for you. Thank you very much. And now over to you, Gustav.
Thank you, Magnus. So as I mentioned in the introduction, in the second part here of the webinar, we will switch focus a little bit and take a look at Opus Suite and what functions and capabilities that we can find in the tool suite that will help us in all phases of naval system design. So what we have done here is taken some of these phases that Magnus mentioned earlier. You can see them up in the top right corner, and focused and just want to give you an idea of how you can use the tools in our suite to answer and address some of the challenges in here from an analytical perspective. So the first one, let's move forward here to highlight the first part, which is the early stages of the design. So in here, one critical question is, of course, the total cost of ownership and what will that look like over the planning horizon. And of course, you can look at it from many different perspectives, but here we show an example of how we can use Catalog, our lifecycle cost analysis tool that uses a bottoms-up modeling approach to capture all the relevant parameters, mostly quantitative, of course, put a number to it, build that cost model from the ground up, and through the tool we can slice the analysis and look at this from many different points of view. So in this example here, up to the left, we can see where will we see our cost over time for this planning horizon. We can look at it per location. At the bottom left corner, typical use case is to compare alternatives, right? It may be two completely different designs that have different, what could it be, operating parameters, different fuel requirements, other capabilities, whatever it may be. And through the cost analysis catalog, we can line them up and compare alternatives from a cost perspective. So this is a prime example of how we use Catalog for these early designs as well. Opus 10 is another good application which can be utilized in the early phases. We have shown in some earlier papers and previous work that you actually don't need all the details to get a fairly good understanding on how your system will perform and what it will cost you. And of course, through the iterative process, you will refine your models and then get better and better estimates and understanding of your performance. Next phase we're going to look at here is the system design phase. Picked some areas there, in this case requirements gathering, mission capabilities, and functions. So one example there is the system of systems analysis, which we can use, of course, in any of our tool, but I would say our simulation, discrete event simulation tool, Simlox, is the best fit for this kind of analysis. And what we mean there is we can look at individual subsystems, individual functions, see how they perform individually, but also together as a system of systems. For example, you may discover that your requirements for each individual subsystem is almost met, but when you put them together, you're not quite reaching the goals for the system of systems. There are, of course, other examples as well. Another type of analysis, which is also on the little bit more detailed level, we're looking at redundancy either within systems or redundancy between systems. And here you have a number of requirements. maybe from the mission and capabilities, or more requirements on the individual subsystems themselves, how they are set to perform. And given the engineering data, we can plug that into SimLogs, run the simulation, and see if the redundancies we have in place will be sufficient, if the redundancies will have an impact on our proposed inventory, etc. Another aspect that it's recommended to start looking at early on in the process is to consider your operations, right? What kind of operations are you supposed to support, and will your design support that operation? Some examples from SimLogs here. What we can see up to the left is our full product breakdown over in the view here, and we'll show a little bit more of that later on. We can focus in on the redundancies and functional block diagrams, model those in detail to be able to simulate how that affects our mission performance, our system performance, etc. We can model detailed operational profiles to see how various op tempos, various periods in port, your time at sea, etc., how that will impact the performance of your system and your support solution as well. In this case, the screenshot in the bottom left corner is taken from an endurance scenario, where we see that during the course of the simulation, we're fully capable at some parts of our operations and during some missions, and due to the endurance aspect of the scenario, we can see that our performance degrade over time. Down to the right, another aspect to look at is what are some of our functional capabilities, and how well are we able to perform and meet our capability requirements. This is a fairly new functionality that we have in the application, that we are pushing out to our customers right now, and hoping that they will be able to take advantage of that. But we believe it's pretty powerful to get an understanding not only how will your actual mission operations be impacted, but what capabilities do you have while you're at sea. As we all know, a ship at sea isn't doing just one thing at a time. It's serving many purposes during the course of its operation. Procurement phase can, of course, mean many different things. Procurements of our systems, procurement of our support solution, etc. From an Opus Suite perspective, we really come down to one of the core questions that we look at here on a high level: cost versus effectiveness. And for that, Catalog is an excellent tool to look at the cost, but when you want to combine the two, Opus 10 is the go-to application, where we incorporate spare parts optimization, which is a significant part of that both cost and effectiveness component. So what that could look like in the specific scenario is that we are comparing two individual ships. We want to see maybe early on in the process, design has been more or less set for each of these ships, or the vendors, OEMs, they have already designed these, and as an operator we need to design what will be the best option for us in terms of procurement, right? So we can model that in Opus 10, run the spare parts optimization, which looks at the system, the support solution, combining that with the proposed operations, and get a clear understanding which alternative is preferred from a cost and, in this case, availability perspective. For those of you that are familiar with our tool suite, you've seen the cost effectiveness curve many times, and it's a central part of the type of analysis that we do. So in this specific case, we can clearly see that one of the alternatives is better than the other, both from a cost and availability perspective. But the analytical capabilities here gives us tools to dive into these numbers and compare and contrast and see where are these differences. perhaps it's not as large of a difference that it appears to be, or there could be, of course, other factors that contributes to these differences. And with Opus 10, we have the means to look at that in detail. Just overall basic detail design, there are, of course, many design choices that will have an impact on your reliability, availability, maintainability, and supportability aspects of your system, right? So this is really the core of our entire tool suite, depending on what type of question it is that you are investigating or what answers you're looking for. Any tool serves their specific purpose. For this example, I wanted to showcase how we can use primarily, once again, Opus 10 to look at design choices as it comes to the support organization, including spare parts, right? So a common scenario is that you're designing your support organization, trying to decide where repairs will happen, where to keep inventory, and so forth. And this can, of course, be for a single ship or for a fleet of ships or a fleet of specific subsystems installed in ships. Of course, many different scenarios are possible here. And what I showcase in this specific example is a vendor recommendation of a spare parts package that they think could be applicable. You run that through the analysis and see that given my proposed operations and my setup, this proposed solution or stock suggestion shown in green here is not as good as promised. We can run another type of analysis where we see what if we had the flexibility to optimize our inventory without any constraints. And that's what you see in the orange line there. We can see there's, in this case, quite a gap between what the supplier suggested and what we think would be the optimal stock allocation. Using some of our specific capabilities in there, we can then see, well, what if we already purchase some of these parts? What can we do to improve our situation? Which parts should we buy next? And so forth. There can, of course, be other changes, modifications that you want to make to your support organization, to your repair alternatives, and so forth. We do have a LoRa module in our tool suite where you can basically give the tools or give the application your alternatives for your maintenance concepts, and we will optimize those for you and present the best solution given the input data. And for those of you that are familiar with our tool suite, you know that sort of a main use and how the workflows are set up is to enable what-if analysis, to enable scenario comparisons, and so forth, right? So we can look at all these proposed changes, alternatives, and see how will it impact what we're doing from a systems perspective, from a support organization perspective, and from an operations perspective as well. So this is just one example of how we can utilize Opus 10 for this kind of analysis in the design phase of a project. Other examples include using reliability data to see how reliability of parts, subsystems, etc., will impact the overall performance. Differences in cost data, what's our sensitivity to fluctuations in cost, etc. So all those aspects can be captured here in our data model. And the last section that we will touch on, and which will also lead us into the modeling sample, is in the operations support, upgrades, and retrofit in that phase, which could be sort of an early stage of a newly produced system, or traditional modeling of sustainment. These can be existing existing ships that's been in use for quite a while, but we want to look at a specific aspect of the operation and get a better understanding of that in detail. And for this, we have Opus 10, of course, which is, as you know, a steady state optimization tool, so may or may not be applicable depending on the kind of analysis. But the dynamics, especially the time dynamics in SimLogs, makes it a good go-to tool for these kinds of analysis. And we also recently added Opus Evo, which gives you the possibility to optimize aspects from a more tactical perspective and not just strategical spare parts optimization. A typical use case here for all these areas combined is to optimize spare packages for deployed operations. So deployed operations in this case means that we leave port, we are able to carry some stock with us, we have capabilities to perform some maintenance on board, and we're going to be out and operating for a relatively short period of time. And we want to see what is it we need to bring with us to do that. What parts shall we bring? What resources do we need for maintenance and so forth? And we can use a combination of tools here to get a good understanding and to see how well we perform. And this type of analysis really leads us into to the modeling example that I will go through. So in this example, we'll touch on many of these areas that I've already mentioned. So we'll show some redundancy modeling. We're looking at an endurance scenario, and it is a system of system model. So this is, although not a produced or a real world model, it is a realistic model that can quite easily be scaled to model a larger system. We do have and model onboard maintenance capabilities and spare parts. We have modeled a DRM, a design reference mission with corresponding mission requirements. Some of the results that we're looking for are, in addition to some of the standard SimLogs results, such as mission performance and system states and reason for unavailability and so forth, we're also going to take a look at system capabilities, tying back to Magnus' presentation about how we can split our larger ship into subsystems, function areas, and so forth. And one of our new features in SimLogs is the ability to look at downtime drivers in order to get a direct connection between the performance of the system as a whole and map that down to individual parts to see individual parts, individual resources, maintenance, and so forth, to see if we have the flexibility to make changes. Where do we want to add parts? Where can we remove parts? What's our bottlenecks, and so forth. So before I start sharing my screen here and go into the live demo, just wanted to give you an idea of how we put this model together. So hopefully you recognize this slide from earlier on, where we divided our main functions and mapped those to capabilities. And if we continue this mapping, we can now introduce subsystems as well, map those to our functions, and then categorize the functions into capabilities. And as you see, for the purpose of this example, I've removed some of the listed capabilities here to only focus at the anti-aircraft warfare, anti-submarine warfare, and the naval mine warfare. So with this mapping, we can now combine the functions. We're not necessarily looking at that in this particular model. So we can get a mapping to see which subsystems are required for each one of these capabilities. And that allows us to get an understanding of how well are we able to perform our capabilities through subsystems, and of course their corresponding composition through parts, and with that sort of the link to the spare parts that we bring on board. So in our models, we're tying all these aspects together, and on top of that, we add the operations, which is what will, at the core, generate failures, generate maintenance need that we need to satisfy, and that will have a direct impact on these capabilities and mission performance. So the scenario here is an endurance scenario. We have a simplified ship with 6 subsystems, and I looked, it's about 300 parts that are part of this model. We do have some redundancy or functional blocks that I will show you here. There is a design reference mission, which in this case is pretty straightforward. We have our endurance period, which I believe is 6 months, split up into smaller slices, each with their own specific requirement. So the focus for this analysis is to look at mission performance, mission capabilities, and then at the end, take a look at the downtime drivers and see, is there anything we can do to our model to quickly improve our performance without any drastic measures? Maybe if we could just identify a few bottlenecks, we can address those and rerun our model and see if we can achieve any improvement. So with that, I'm going to start sharing my screen and jump into the live demo. Okay, so here we are, jumped out of PowerPoint world, and we're in Simlox now. So what we have here is, well, some of you may have seen this before or are familiar with our tools, but a quick sort of just orientation on what it is we see here. We have modeled a ship. So as I said, the ship here is a system of systems, and we have captured a number of subsystems. So the 6 subsystems that you saw in the previous matrix are listed here. And under each one of them, we have a basically an LCN with the corresponding parts. And if we were to look at each part, we can go and look at the maintenance procedures for each of these parts. So we modeled the product breakdown here. Some of these, such as the air and missile defense system, has some redundancy model into it. So in this case, we have a simple parallel redundancy, saying that we need, well, in this case, we actually need all 4 of them, but we could easily say that we only need 3 out of these 4 antenna arrays, for example. And looking at the antenna arrays themselves, they too have redundancies in them. So we have support for modeling nested redundancies in here to capture all these redundancies, which are typically or commonly found in ships, especially when it comes to radar arrays and those kinds of systems. But also when it comes to engines, generators, whatever it may be, there is not only a redundancy, but there's also opportunity or possibility to operate in degraded states and still be able to satisfy your requirements. Perhaps maybe a little bit different in some other domains where redundancy means that you're going to stay alive, or you're going to have the capability to abort your mission and go back to your base. But with ships, and especially being such large platforms, there's typically opportunity to address issues while you're at sea. So now we looked at the product breakdown. In this case, we're not really focusing on the support organization. We can see that the ship, most of the activities here happen at the ship. We have a home port with some capabilities as well. But given that this is an endurance scenario, we're not really focusing on the maintenance ashore. Looking at the DRM scenario, we're only considering one ship or one system, so it makes it look pretty steady. But if we were to look here and change, we can see that our scenario is a 6-month endurance scenario. Over to the left, excuse me, we have all our tables represented in their categories. So we have all our reliability data already modeled. We have our parts modeled in the tables here. We have our maintenance tasks with their properties, reorder capabilities, onboard capabilities, all that also captured in our model. So as you can see, depending on what you need to model, there are a lot of flexibility and options in SimLogs to actually capture that in your model. Not saying that you always have to specify all these details for every model, but in this stage of the life cycle, we typically have a lot of details to take into account. We know the operations, we know the requirements in detail and so forth. So we're able to capture that. Also, we have been provided with some inventory that we modeled that we carry with us on board the ship. And this is some of the leverage we have to play around and to do things in our model, right? To look at, are these the right parts? Is there anything we can do to improve this and so forth? So now that we've seen the input that's needed, or at least portions of it, we can run this simulation and see what happens. So I'm going to run this, save and run it here. So in this case, I'm running 200 replications. And what I'm going to do is I'm going to switch gears and look at the results over here. This is our fairly new interface for looking at results, which gives a little bit more flexibility in seeing the results from the simulations. So in this case, some of the traditional result we're looking at is mission performance, both over the entire scenario. But for an endurance scenario, it's typically interesting to look at it over time, right? And we can see here how our performance degrade. Another key area to look at in the simulation to gain insights is to look at system states, right? So in this case, our system can be either fully capable, we can be partially capable, or rather not fully capable, and we can also be unavailable. And when we're unavailable, we can go over here and see what are the reasons for unavailability. In this particular model, we can see that we're unavailable due to active repair or waiting for items. So this portion sort of is affected by our spare parts. But in other models, and if we show that too, we can see other reasons for unavailability that we're also tracking, just not in this model. For example, preventive maintenance, transportation in models where we're actually transporting our systems to perform maintenance. We can be waiting for resources. We can have admin delays. So there are, of course, several reasons for unavailability, which we can dive in, look into detail here, depending on what the scenario and what the analysis is. So these are traditional SimLogs results that if you've used the tool before, you're familiar with. Some of the newer results here, actually, I do realize I forgot to show something. So let me go back. Here to our input. So one more thing I wanted to show is what about these capabilities that we saw in the presentation? Where are those models? So they are modeled here as what we refer to as operational modes. So what we're interested to looking at here is our anti-aircraft warfare, submarine warfare, and mine warfare, and see how we're able to perform these. So what we're specifying here is that we're collecting results for these specific capabilities, right? And what we've done in some of these data tables is that we have tied those subsystem requirements to these individual capabilities, right? So depending on how our subsystem perform, we're either capable or not capable for either one of these. So we're collecting those results as part of the simulation. And now that I made that clear, let's go back here so that you're following what it is that we see. So in this this chart over to the left, we can see for these three areas, how well are we meeting or how are we performing with respect to these capabilities, right? And this is over the entire 6-month scenario. So for the mine warfare, we can see that we're capable with these subsystems in 63% of the time. For anti-submarine, 65%, and for anti-aircraft, 50%, roughly 50% of the time. Right, so we can get an understanding on how well are we able to meet the requirements for these capabilities, and what tasks are we able to perform, right? So this gives you a lot of power to look at not only one at a time, but you can define basically how many capabilities you want, and you'll be presented with how well you're able to meet those requirements. We can also look at those results over time. So as I alluded to before, we're looking at an endurance scenario. So we can see here after maybe 3-4 months, our performance is significantly degraded. So perhaps if we carried some more stocks, we would be able to push a little bit further, or maybe we are sort of we are happy with how we're performing over time for these specific capabilities. Just wanted to show that capabilities do not only have to be defined for a number of subsystems. We can look at individual subsystems by themselves and look at capabilities for each one of these. So these are the torpedo system, the six subsystems. How well are we meeting the capability? And it's pretty clear here that our propulsion system and our air and missile defense system are really the ones that's impacting our overall capabilities, right? So we can see air and missile defense 55%, propulsion 67%. So now we didn't know this going in, right? We just modeled our subsystem, our operations, but through the simulation here, we're able to see which of these subsystems is it that really has an impact. So naturally then comes the next question: what do we do to address this? If this is how we're performing, how can we use the tools to find areas to improve, or simply to understand what's going on? So with the most recently release of SimLogs, we have added capability downtime drivers, or simply downtime drivers. So for each one of these capabilities, we can look at, well, we're either capable, everything's fine, or we're down, we're not capable. And in that case, what is it that's contributing to that? So we can look at it from a subsystem perspective. So in this case, for our naval mine warfare, we see that propulsion is really the driver. Similar for the anti-submarine warfare. But for our anti-aircraft warfare, we also have something going on here with the air and missile defense system that we may want to take a look at, right? Propulsion is still up there. If we could address that, that would probably improve our overall capability. But we have more of the subsystems that are now impacting the downtime. And do note here that once the system is down, It can, of course, be for many reasons, right? It could be that both your propulsion and air and missile defense is down, or one at a time, or it could be redundancies between, maybe not these systems, but in the general sense, redundancies between systems that make multiple subsystems or multiple parts contribute to downtime. And we're capturing all of that in here, so we're able to map it down to the individual subsystems, and furthermore down to the individual parts. So in the last step here of the demo, what I will do, instead of adding the item downtime drivers, so we've seen the subsystem downtime drivers here. Let me just open what I prepared. We don't have to save this one. We'll just add the item downtime drivers here. So we see the subsystems, and then for each one of these, I have added the individual items. So in this case, they are represented by a number. So looking at both from a capabilities perspective, but also the individual subsystems perspective as well. So we can clearly see here for propulsion, our part 601113 is really the main contributor, right? There are some other parts that contribute as well. For the air and missile defense, we see it really comes down to one part here. And if we were to look at this in a little bit more detail, we see that it's our antenna array which is made up of a number of antennas, right, with quite complex redundancies. So that requires some additional detail to understand how that all fits together. Maybe not adding spare parts is the only thing we need to do, but let's address that later. So for this specific part, what can we do now? Well, let's try this. Let's rearrange the windows so we can have both our input, our simulation, and the results here. Let's go back to the capabilities, and we'll see how these results. So we have 63, 65, and 50% here, and we see our propulsion is at 67.5%. If we instead went over here and said, let's see, I can find it here. So this is our part, right? 601113, and we're already carrying 12 on board the ship. Let's say if we had the flexibility to bring a few more, let's say 15, maybe at the expense of some others that we can identify that are non-critical, we could add some more parts to it, and we can rerun the simulation here. And when it's done, I would expect these to jump up, to change, right? And we see they do. They moved from 63 and 65 up to 60, what's this, 66 and 69 almost. So all I did was really change the quantity of a few parts, and I can see quite a significant increase in our capabilities. Of course, for a larger system and a realistic case, it may not be as straightforward as it is for this demonstration case, but hopefully you get the point and understand sort of what it is that's going on here. So looking back at the downtime drivers, we can see that, let's see if these update here. We can see that our part 601113 is no longer the most contributing downtime driver. We have other parts now that are contributing more. So we can iterate this process and look at how can we find the best stock allocation. Of course, this in itself can be a cumbersome process if you wanted to do this over and over, but that's where we have Opus Evo that can do this for you, right? Where you can basically let Evo run and optimize against this and propose the optimal spare package that will minimize your downtime overall. So with that, let me jump back into the slideshow to wrap the presentation up. Okay, so now we're back from the live demo and back into PowerPoint world again. With our last slide, which is really wrapping this webinar up with what we believe are the takeaways from what Magnus and I have presented. So we want to emphasize here that data-driven decision-making is, I wouldn't say required, but it's encouraged in all phases of the life cycle of the system. Even in the early stages where you may not have as much data as you think or as much experience, there's always the possibility to do modeling to understand the system, the future in greater detail. And of course, as part of that iterative process, you will always refine your models, refine your analysis, and get better and better understanding of your system. And of course, it's in our interest to show what Opus Suite can do to help you and what tools we have that are useful tools for maritime modeling in particular, but all kind of systems engineering and systems modeling in general. We've showed some specifics of Simlox, but also given you a taste of Catlock and Opus 10 as some other tools that will help you in your with your analytics. And lastly, we saw a live demo that you hopefully enjoyed that shows more specifically what functionalities we have in Simlox, our discrete event simulation tool that will help you to support your maritime system design and lifecycle management. So with these takeaways, we have now come to the conclusion of the presentation, and I would like to take the opportunity to thank you everyone for attending the webinar today. We appreciate your time and participation. And as pointed out, if you have any questions, feel free to write them in the chat or reach out to us at Systicon, and we'll be happy to get back to you. So on behalf of Magnus and Systicon and everyone that's been here, I want to thank you for joining us today and wish you a great rest of your day.
Thank you.